Hi, good afternoon or good morning or whenever you're watching this. My name is Jada Wilson, and today I will be presenting to you my final chemistry project. My two reactions were Prinz reaction and Robinson's annulation. I will be starting with Prinz reaction and then moving on to Robinson's annulation. So I'm just going to go to the analysis steps because that has everything that I want to talk about. So step one is the pronation of the aldehyde. The alkane, which is this one right here, is reacting as a nucleophile and is attacking the uncharged oxygen. The oxygen has a formal charge of +1 and pulls the electronic pair towards itself. The -1 charge then attacks the other carbon and becomes part of the reaction, and the second carbon is now the electrophile. So here we have the nucleophile with a -1 formal charge, and here we have the electrophile with a +1 formal charge. And as you can see also in this reaction, we see a leaving group of H2O, and here you see the transfer of the double bond and is going to be moving to this carbon over here. And you can see the double bond over here is going to be moving to the F1 charge of the oxygen, thus creating another lone pair for that oxygen. Step two is the formation of the intermediate. So again, like how I explained, you see the double bond moving to this carbon and this double bond moving to the oxygen. And in result, you get the joint combination of the final product, or not the final product, but basically this is the transition and this is the intermediate. So the alkene attacks the aldehyde, which creates a beta hydroxyl carbon intermediate. Here's the beta hydroxyl carbon intermediate. And as you can see on carbon 2, you see a positive charge, meaning that the carbon does not have a full pair or a full set of 4. And then as you can see, basically the reaction that happened, as you can see, the double bond then transferred over here, which gave us the R3 right here. And then the oxygen from this one has, the double bond from the oxygen has moved here to give us another lone pair. The difference in products. So basically there's 3 different products that can come from this Prinz reaction. So I did every single step. So we start from the carbocation intermediate and we move to here. So if there is no additional reagents, the intermediate reacts with water, H2O, creating an elimination reaction, which we would be eliminating H3O, and this would be the loss of a leaving group over here. And then this would produce an allylic alcohol. So as you can see, this lone pair of the oxygen from the H2O is going to move to this hydrogen, and then the hydrogen bond right here is now going to be forming a double bond over here. And this would also allow this carbon to now have a complete 4, so it is no longer missing an electron or a lone pair. And then again, the loss of the H3O. So that's one way. And if there is another reagent or another nucleophile, the nucleophile would directly attack the carbocation, as seen over here, causing the carbon to attach to the nucleophile to become neutral. And this process would allow the reaction to produce an alcohol. So as you can see, the nucleophile over here would then attack the carbocation, which would also be the electrophile again, and then which would create this, so it could be a neutral charge again, and then you would have the final product as an alcohol with the nucleophile attached to it. And if both of those situations don't happen, then we have the final situation or final product, which I'm going to zoom in for. And if the excess aldehyde from the previous reaction is used, it will create a 1,3-dioxane reaction. So basically, here is the aldehyde, and it has the oxygen. It's taking one lone pair from the aldehyde, and that is going to be moving to this carbon over here. And so the excess aldehyde is then converted. The oxygen from here, again, is going to be moving to R4, and then the double bond here is going to be broken and only having another set of electrons over for the oxygen here. This would then create this formation, and you would see an H2O coming over and adding onto it, which would be like another nucleophilic attack, low-key. So you would see the lone pairs from the oxygen attack the hydrogen, and then the hydrogen bond moves to the oxygen. And so we would then have a loss of, here we go. We would then have a loss of the leaving group, which would be another H3O. And then we would have the final product of 1,3-dioxane. And then for our Robinson's annihilation here, the first things first would be conversion. So the starting reagent would be a ketone. A strong base would need to be used to convert it to an analyte. This will allow the other reagent to be added and continued, through Michael's addition. And so here we have a double bond over here. The double bond is now going to be broken and moved over to this side of the carbon, which would be with the strong base used. And once the strong base is there, our oxygen would have a negative formal charge, and this oxygen up here would have a positive formal charge. And so the lone pairs of this oxygen would then move to the double bond from this portion of the analyte will move to over here. And so basically, this would become our ketone, or this analyte would become our nucleophile, and then over here would be our electrophile. So Michael's addition, with the addition of another reagent, as done before, or here it is, the analyte would become the nucleophile. So this is the nucleophile, and will attack the Michael's acceptor, also known as the electrophile, and this would create Michael's additional product. So here would be Michael's addition, and here would be the final product of that. But as you can see, the oxygen gives away one of its lone pairs to form a double bond, which is over here. And then this double bond would move over here to the electrophile, and the double bond up here would go to this carbon. And this double bond would then move to the oxygen, creating another charge. And then for Adels condensation would be next. And so after that Michael's addition product is made, to finish the cascade in an intramolecular Adel condensation, which would be needed. So here you can see, once the Adel product is made, we create a new bond over here, because this would be a negative charge, this would be a positive charge, and then the bond would stick. And then over here, we then created the double bond as proven before. And then here we would use heat and an ketone to create this. So basically over here, what's happening is this bond, or this carbon, is going to bond with the double bond over here with the oxygen, forming a new double bond here, as well as the already new bond over here. Excuse me. The functional group changes. So there's a reduction in the carbon-carbon double bond and the carbon-oxygen double bonds, and the heterogeneous catalyst or hydrogen gas would be used to do this. After the reduction, we would then finally get the targeted molecule once heat is added. So here you can see the double carbon and the double carbon oxygen bonds are here. And then because of the hydrogen gas attacking, we then reduce the two double bonds to a single bond, which would then give us our final product. And this concludes my presentation. Hope you have a wonderful day, night, week, everything. Have a wonderful break. Thank you again.